Hello, my dear students. Welcome to the session. Continuation of important observations from power electronics concepts. In this session, with respect to Module 2 rectifiers, that is AC to DC converters, I would like to discuss about concept of single phase half wave control rectifiers. All of you concentrate. Friends, we know that thyristor rectifiers is also called phase control rectifiers because in these rectifiers, by controlling firing angle alpha, we can control the output voltage. That's the reason why thyristor rectifiers is also called phase control rectifiers. First, we have to start with the single phase half wave rectifier, or it is also called half wave control rectifier. Single phase half wave control rectifier. Half wave. But point to remember, students, half controlled is different, half wave controlled is different. Half wave means only one device. Half controlled means combination of thyristors and diodes. That is called semi-converter. Later on that you will see. Here I am discussing the half wave control. Don't confuse. Half wave controlled rectifier or simply half wave rectifier. That is also correct. Using R load, resistive load. This is the circuit configuration. Sometimes they will give the through transformer or directly source also they will give. Through transformer, if any problem is framed, directly don't use the primary voltage. You have to convert that primary into secondary voltage. That is, you have to calculate the secondary voltage using turns ratio. If the supply voltage is given, then directly you have to take that voltage is the secondary voltage or supply voltage only. First, we have to concentrate with what is the operation. Positive half cycle, thyristor will conduct alpha 2 pi. Then thyristor conduction angle is pi minus alpha. Negative half cycle, thyristor is reverse blocking mode. Output voltage 0. Output current is also 0. Then what is the peak inverse voltage across the SCR? Vm. These points mainly you have to concentrate. Very important. Single phase half wave control rectifier. Using R load, using resistive load, what is the SCR conduction angle? Pi minus alpha. Very, very important. What is the peak inverse voltage? For resistive load, half wave rectifier, peak inverse voltage is Vm. These are the waveforms. No need to concentrate on the waveforms. Just by considering the firing angle, positive half cycle, you can get the output voltage. Negative half cycle, there is no output. Again, positive half cycle, we can get the output voltage. And you have to concentrate on the voltage across the thyristor waveform also. But mainly very important for gate point of view, analysis point of view. Even in the diode rectifier also I told already, you have to concentrate only on the analysis. What are the formulas that I given with respect to analysis point of view, and what are the problems that I solved, that only you have to practice, friends. For time being, this is for quick reference point of view that I am giving. That's the reason why mainly concentrate on the analysis and what are the practice questions that I done. 99.99% we can expect the questions only what are the questions that I solved in practice. That is in single phase half wave control rectifier using resistive load, peak inverse voltage Vm, circuit turn off time pi by omega, SCR conduction angle pi minus alpha. What is the average output voltage? Pi star, gunshot formula. For single phase half wave control rectifier, average output voltage is Vm by 2 pi into 1 plus cos alpha. Then what is the average load current? V0 by R. We know that the range of firing angle, generally for single phase rectifiers, the range of firing angle is 0 degrees to 180 degrees. It is a 0 degrees to 180 degrees. If alpha equal to 0 degrees, we can get the maximum average output voltage. That is when the average output voltage is maximum for alpha equal to 0 degrees. When the average voltage is 0, for alpha equal to 180 degrees. For alpha equal to 180 degrees, in a single phase half wave control rectifier, the average output voltage is 0. That is what is the observation here. By controlling firing angle alpha, we are controlling output voltage. That's why the name is given as a phase control rectifier. We may expect the question for different firing angles, what is the average output voltage? What is the maximum average output voltage? Then you take alpha 0. Then what is the minimum average output voltage? You take alpha equal to 180 degrees. Yeah, this is important observation. Average output voltage formula is very important, and this is the average output current. We also concentrate on RMS output voltage formula. In single phase half wave control rectifier or half wave rectifier, it is also called one pulse converter. half wave control rectifier na is also called one pulse converter. Why? How many number of pulses per cycle? One pulse. That's why it is one pulse converter. Sometimes they don't give the name is a half wave control rectifier. Sometimes they will give the name with a one pulse converter also. That point also you remember. One pulse or single pulse converter. One pulse converter or single pulse converter. That you have to concentrate. Next very important formula, RMS output voltage. That is Vm by 2 root pi minus alpha plus 1 by 2 sine 2 alpha whole to the power of 1 by 2. This is very important formula because nowadays the trend in GATE exam, it is asking what is the output power. To calculate the output power for resistive loads, you know the RMS output voltage. That is very important. This is the RMS output voltage formula, students. For easily calculation of RMS output voltage, use this generalized formulas that I already explained in the diode rectifiers also. Using this generalized formula also, you can solve this one. Then once you know the RMS output voltage, what is the RMS output current, what is the output power? This is very important. Maximum, the question we can expect by giving the resistance value, it is asking that what is the output power? V naught RMS square by R. To solve this problem, you have to remember this formula. Then what is the input power factor? Input power factor equal to V naught RMS by Vs. Where V naught RMS is the RMS output voltage. Vs is the RMS value of supply. Then what is the voltage across SCR at the instant of triggering? Voltage across the SCR at the instant of triggering is Vm sin alpha. Important. Source current waveform is pulse waiting DC. At every half wave rectifier, no need to remember the source current waveform. I already explained in the input performance parameters. That is, for all half wave rectifiers, any load, the source current is pulse waiting DC strength. Like that you have to remember. Then you have to practice this question. That analysis, what are the formulas that I given, and practice this question. Minimum try to practice these questions. This is your final preparation for power electronics for your GATE exam. Just you have to practice this question. What are the power absorbed in the heater element and supply power factor? What are the peak inverse voltage and circuit turn off time? If the average output voltage is equal to half of the maximum possible average output voltage, calculate the firing. But in this problem, directly resistance value is not given. They given heater load. Heater is the load data it is given. We know that heater is the example of resistive load. Then by using this heater rating, you have to calculate the resistance. Sometimes they will give the resistance value. If heater load is given, even though they don't given the resistance value, from heater rating, you have to calculate the resistance value. Once you know the resistance value, use this RMS voltage formula. Then you have to find the RMS output voltage. Once you know the RMS output voltage, then power output equal to V naught RMS square by R. That's how power output I got 250 watts. Then you have to calculate input power. If any question is asked, calculate input power factor. V naught RMS by Vs. This is 0.5 lagging for this problem. For the peak inverse voltage, Vm. Vm is root 2 Vs. Given supply is the RMS value of supply, that is 200. Then what is the circuit turn off? Given that average output voltage is equal to half of the maximum average output voltage. When the output voltage is maximum for alpha equal 0 degrees, I got V naught equal to V naught maximum, that is Vm by pi. Substitute here, then simplify this, you have to calculate the firing angle. This is one model of question that you have to consider. And one more important model here, this is important. Sometimes they will give the average output voltage, calculate the firing angle. One method is by giving the firing angle, you have to calculate average output. By giving the average output voltage, you have to calculate the firing angle. These two models are important ones that you have to concentrate. That is, in single phase half wave control rectifier, what is the average output voltage? Very important formula. That is V naught equal to Vm by 2 pi into 1 plus cos alpha. V naught equal to Vm by 2 pi into 1 plus cos alpha. What is the RMS output voltage formula? That two formulas mainly you have to concentrate. What is the SCR conduction angle? Here only one SCR. That's why what is the SCR conduction angle? Pi minus alpha. The next one is single phase half wave rectifier with the RL load swings. RL load combination. Here also mainly you have to concentrate. This is the positive off cycle thyristor will conduct. Thyristor will conduct alpha to beta. That's why what the SCR conduction angle? Beta minus alpha. The SCR conduction angle is beta minus alpha. Mainly you have to concentrate instead of waveforms. Waveforms is not that much of important, but you have to concentrate on voltage across the thyristor waveform. Then this is important. For the peak inverse voltage Vm, for the circuit turn off time 2 pi minus beta by omega, for the SCR conduction angle beta minus alpha, for the average output voltage. In RL load case, the average output voltage equal to Vm by 2 pi into cos alpha minus cos beta. But the average output current that you have to concentrate. But the RMS output voltage, that is Vm by 2 root. Sometimes direct formula also we can expect. Vm by 2 root pi beta minus alpha plus 1 by 2 into sin 2 alpha minus sin 2 beta whole to the power of 1 by 2. Then what is the output power relation? What is the input power factor relation? Source current is pulsating DC. And this formula also you have to remember. What is the voltage across the SCR at the instant of triggering? The voltage across the SCR at the instant of triggering, that is Vm sin alpha. But the voltage across the SCR at the instant of current decays to 0, where the current falls to 0 at extinction angle. That's why Vm sin beta. These two formulas also important. Even circuit turn off time also very important for this case that you have to concentrate. And one more observation from RL load. We know that if the load is consist of inductance, there is a possibility of transients. Now the question is, without any transients, at what firing angle thyristor you have to trigger? And one more possible question is, at what firing angle the transient currents are maximum? For this, these two formulas you have to remember. Derivation no need to concentrate. Case 1. During triggering of SCR, to eliminate transient currents, at what firing angle you have to trigger the thyristor? At alpha equal to pi. What is the pi here? Pi is the power factor angle. That is tan inverse XL by R. That is XL is nothing but omega L. That is, if the firing angle equal to power factor angle, there is no any transient currents. If SCR is triggered at power factor angle, there is no transient current. Then when the transient currents are maximum in RL load case for half wave control rectifier, if firing angle equal to 90 plus pi, the firing angle equal to 90 plus pi, then the transient currents are maximum. If for example, by giving the circuit like this, if the question is asked, at 0 transient currents, what is the firing angle? Alpha equal to pi. That is tan inverse XL by R. XL equal to 50. R is also 50, 45 degrees. At maximum transient condition, what is the firing angle? Alpha equal 90 plus pi. 90 plus 45, that equal to 135 degrees. That is, in this circuit, if you trigger the thyristor at 135 degrees, the transient currents are maximum. In this circuit, if you trigger the thyristor at 45 degrees, there is no transient currents. That type of questions also very important. And you have to practice these questions. This is the problem with respect to RL load. You may expect what is the circuit turn off time, what is the average output voltage, what is the average output current. Next. One more important configuration with respect to single phase half wave control rectifier, that is RL and freewheeling diodes. Very, very important. In RL and freewheeling diode, SCR conduction angles are important. Freewheeling diode conduction angle is important. In RL and freewheeling diode, SCR conduction angle is pi minus alpha. But freewheeling diode conduction angle is pi plus alpha. Let us assume that it is a continuous mode of operation. What is the SCR conduction angle? What is the freewheeling diode conduction angle? These are the waveforms with respect to continuous mode of operation. This is the freewheeling diode current waveform. This is the thyristor current or source current waveform. This is the voltage across the thyristor current thyristor voltage waveforms. Mainly conduction angles you have to concentrate. Peak inverse voltage Vm, circuit turn off time pi by omega. But I already explained, even in the diode rectifier also I given one statement. With the freewheeling diode, most of the formulas are similar to R load, but except conduction angles and current related formulas. With the freewheeling diode, same that of R load except current waveform analysis. This is very important, students. SCR conduction angle in a continuous mode, that is pi minus alpha. Freewheeling diode conduction angle pi plus alpha. In discontinuous mode, still not framed in gate exam with respect to discontinuous mode conduction angles, we may expect you ready to answer. Discontinuous mode for beta greater than pi. Discontinuous mode, but condition is beta greater than pi. SCR conduction angle is pi minus alpha. Freewheeling diode conduction angle is beta minus pi. Discontinuous mode is beta less than pi, students. Discontinuous mode beta less than pi. SCR conduction angle is beta minus alpha, but the freewheeling diode conduction angle is 0. For beta less than pi, even though it is RL load, the freewheeling diode will not conduct. Very important observations. Mainly in this circuit, the conduction angles are very important. Then average output voltage is similar to R load formula. That is V0 equal to Vm by 2 pi into 1 plus cos alpha. The average load current I0 equal to V0 by R. This is RMS output voltage. RMS output voltage is equal to Vm by 2 root pi into pi minus alpha plus 1 by 2 sin 2 alpha to the power of 1 by 2. Then what is the RMS output current? Let us assume that it's a continuous mode of operation. The RMS output current equal to average load current. Then output power. Wherever the continuous mode I am discussing with respect to rectifiers, you have to calculate the output power is V0 into I0. Don't take V0 RMS into I0 RMS. You have to take the V0. In a discontinuous mode, you have to take V0 RMS into I0 RMS. But in a continuous mode, V0 into I0. Then what the average thyristor current? Thyristor conduction angle is pi minus alpha. That is pi minus alpha by 2 pi. What the RMS thyristor current? You take square root. But the average freewheeling diode current? Freewheeling diode conduction angle is pi plus alpha. That is I0 into pi plus alpha by 2 pi. But the RMS freewheeling diode current? I0 into square root pi plus alpha by 2 pi. What is the input power factor? This is the 5-star form. Input power factor equal to V0 into I0 by Vs into Is. Voltage across SCR at the instant of triggering is Vm sin alpha. These analysis points are very important with respect to single phase half wave control rectifier with freewheeling diode. With freewheeling diode, this is the I0 expression. This is not important for gate point of, but I already explained RL load. When the transient currents are maximum, when the transient currents are minimum, that only very important. That you have to concentrate. Then with respect to RL and freewheeling diode, this problem you have to practice. In this problem, average output voltage they given, you have to calculate the firing angle. Average output voltage is similar to R load formula. Na? V0 equal to Vm by 2 pi into 1 plus cos alpha. You have to equate to the average output voltage. From this you have to calculate the firing angle. And this is very important. All these are the expected models of questions. We may expect what the average thyristor current, RMS thyristor current, what the average freewheeling diode current, what the RMS freewheeling diode current, what the input power factor, all this we can expect. Then first I calculated what the average output voltage, what the average thyristor current, what the average thyristor current. Next, what the average freewheeling diode current. All the formulas I applied. RMS freewheeling diode current, input power factor. So input power factor is V0 into I0 by Vs into Is. Then I calculated Is. Then you have to calculate input power. Please practice these problems. If any question is asked from single phase half wave control rectifier with freewheeling diode, these models of questions are very important. And one more configuration of single phase half wave control rectifier is also called one pulse converter. It is also half wave rectifier. Half controlled is different, students. Half wave is different. Half wave means only one device with RE load. In RE load case, that already you know, analysis only it is very important. What the peak inverse voltage Vm plus E? What is the circuit turn off time? Pi plus 2 theta 1 by omega. Circuit turn off time is pi plus 2 theta 1 by omega. What is the minimum possible angle at which SCR is triggered? Theta 1. Less than theta 1, we don't trigger. Minimum angle is theta 1 or greater than theta 1, you can trigger. Then SCR conduction angle is alpha to theta 2. For RE load, it conducts alpha to theta 2. Then what the average load current I0 expression? What the average output voltage? What the RMS output current expression? What the power delivered to the battery? What the total output power? What the input power factor? Directly formula also we can expect. Input power factor. What the battery charging time? Voltage across the SCR at the instant of triggering. If it is not a RE load, if the load does not consist of battery, the formula is Vm sin alpha. If the load consists of battery, Vm sin alpha minus E. This observation is important. And this is the average load current formula also that you have to concentrate. And this problem you have to practice. This expected model of question. But I am not telling that they will give the same values. But I am giving the guarantee, 99.99% guarantee I am giving. We may expect the model, same model, but values may be different. This is the formula for average output current. Then use this formula. You have to calculate average output current. Then once you know the average output current, you have to calculate average output voltage. Theta 1 is sin inverse E by Vm. What is the minimum angle at which SCR is triggered? This is the theta 1 I got 4 degrees, but the given firing angle is 30 degrees. If firing angle is not given, minimum angle you have to take the theta 1. Then peak inverse voltage is Vm plus E. This is about single phase half wave control rectifier with RE loads. One more configuration of single phase half wave rectifier with RLE load. RE load and RLE load, only difference is where alpha to theta 2, but here alpha to beta. That's the only difference. In RE load, alpha to theta 2, but in RLE load, alpha to beta. Because of inductor, a beta will come. Then this is the waveforms. Waveforms is not important. No need to practice this. Directly go for the analysis. Single phase half wave rectifier with RLE load, peak inverse voltage Vm plus C. Circuit turn off time 2 pi minus beta plus theta 1 by omega. 2 pi minus beta plus theta 1 by omega. SCR conduction angle is beta minus alpha. This is the average current expression. This average voltage V naught equal to E plus I naught into R. Then what is the RMS output current? What is the power delivered to battery? Power delivered to battery is E into I naught. Load power is E into I naught plus I naught RMS square into R. Input power factor. Battery charging time. Minimum try to remember these 5 formulas. Up to this 5 is important. And this also important. What is the voltage across the thyristor at the instant of triggering? Vm sin alpha minus C. What is the voltage across the thyristor at the instant of current decays to 0? Where the current falls to 0, beta. That's why Vm sin beta minus C. Vm sin beta minus C. But this average current expression is there now. We can also concentrate on simplified formula of average current. We can also use this formula directly. If you are unable to apply this formula, making integration you are feeling very difficult, then directly go for this formula. That is average output current of half wave rectifier equal to Vm by pi r into sine of alpha plus gamma by 2 into sine gamma by 2 minus E gamma by 2 pi r. You have to apply this formula for any load. Even for RE load also you have to apply this formula. RE load also. But gamma is different. In RLE load, what is the gamma? Gamma equal to beta minus alpha. For RE load, gamma equal to theta 2 minus alpha. Theta 2 minus alpha. That is 1 and 2 applicable for RLE load. Even for RE load also we can apply. But in RE load, what is the conduction angle? Gamma equal to theta 2 minus alpha you can apply. That is, instead of using this formula, average output current, you have to directly use this simplified formula. You can easily get the answer. But only conduction angle is RLE load means beta minus alpha. RE load, that is theta 2 minus alpha. Theta 2 minus alpha. So that you have to concentrate. Actually in RE load I solved one problem. This one. In RE load case, to calculate the I naught, I solved this problem. This one. This much of steps are there. Or simply you can also apply like this. Or I naught equal to is Vm by pi r sin of alpha plus gamma by 2 sin gamma by 2 minus E gamma by 2 pi r. This formula correct now? That is minus E gamma by 2 pi r. This one. Vm by pi r into sin of alpha plus gamma by 2 sin gamma by 2 minus E gamma by 2 pi r. But point you have to remember, by using this formula also, we can get the same answer. Try to solve this one. But what is the gamma here? For RE load, gamma equal to theta 2 minus alpha. Gamma equal to theta 2 minus alpha. But during applying this formula, this value you have to substitute. Gamma is here radian. This gamma must be in radian. Sin of function gamma is degree, but here you have to substitute the radian value. That observation is important. Like this for any load also, for RE load also, that formula is applicable. But once you know the I, but no need to remember this V naught formula. Just remember the I naught formula. Once you know the I naught, then directly calculate V naught equal to E plus I naught into R square. This is about single phase half wave control rectifier using RLE load. Try to practice these questions. 5 star. Minimum try to practice analysis formulas and practice the question. That is your final preparation for power electronics. Yes, this is the theta 1. Minimum angle at which SCR is triggered. Then what the circuit turn off time you have to calculate. What the average output current. What the average output voltage that you have to consider. Next, one more configuration of half wave control rectifier is single phase half wave control rectifier or half wave rectifier with RLE and freewheeling. Friends, even in the diode rectifier also I given one statement. RL and freewheeling diode and RLE and freewheeling diode. The analysis and waveforms are same. Only difference is I naught formula. That is, in this case I naught equal to V naught minus E by R. But V naught formula remains same. V naught equal to, that is Vm by 2 pi into 1 plus cos alpha only. Vm by 2 pi into 1 plus cos alpha. That only difference is in RL and freewheeling diode V naught by R. But in RL and freewheeling diode V naught minus E by R. Let us assume that it is also continuous mode of operation. Even though load consists of battery, you don't take it as a theta 1, minimum angle. Very important. Actually, if the load consists of battery, minimum angle is theta 1. But in continuous mode, it is not theta 1. We can also trigger the SCR at 0 degrees also. That is, in continuous mode, even though load consists of battery, the effect of battery is not considered. There is no concept of theta 1, theta 2. Then this is the formula, same formulas it is repeated. Whatever RL and freewheeling diode I given, same formulas are repeated. But only this formula is different. RL and freewheeling diode, V0 minus E by R. This is the RMS output voltage, this is the RMS output current. Then what is the output power, what is the average thyristor current, what is the RMS thyristor current, what is the average value of freewheeling diode current, RMS value of freewheeling diode current, input power factors. All these formulas similar to RL and freewheeling diode, but except I0 formula. Then this also you have to concentrate. A single phase half wave rectifier with purely inductive load. Already based on this circuit, 2 times repeated in gate exams. In this case, what points mainly you have to concentrate? What is the extinction angle? What is the conduction angle? The extinction angle is 2 pi minus alpha for purely inductive load. The conduction angle is 2 into pi minus alpha. But the average voltage across the load is 0. Wherever the pure inductor is there, what is the average voltage, friends? The average output voltage V0 equal to 0. Pure inductor na, the average output voltage equal to 0. Only important observations are here. If you want, remember the I0 formula. This is the I0 formula. But what is the extinction angle? 2 pi minus alpha. What is the conduction angle? 2 into pi minus alpha for half wave control rectifier with purely inductive load. Then if you find the average output voltage, positive area equal negative area, na, the average output voltage is equal to 0. What is the quadrant operation of single phase half wave control rectifier? Single phase half wave control rectifier is operated always in the first quadrant. Very important. For any firing angle for 0 degrees to 180 degrees. For any firing angle for 0 degrees to 180 degrees, always V0 positive, I0 positive. Always voltage positive, current also positive. Voltage positive, current positive means which quadrant? First quadrant. That's why a single phase half wave control rectifier is a single pulse and single quadrant converter. But it is which quadrant? First quadrant. Single pulse, single quadrant converter. Na? Which quadrant converter? This is the first quadrant converter. If it is the first quadrant converter, V0 greater than 0, I0 greater than 0. That is for half wave control rectifier, always V0 greater than 0, I0 greater than 0. V0 greater than 0, I0 greater than 0 means V0 is positive, I0 is positive. If V0 positive, I0 positive, always power is positive. If the power is positive means power is delivered from source to load. That's the reason why it is used only for motoring current. That is single phase half wave control rectifier is used only for motoring control. It is not used for braking mode in that application. Because always V0 positive, I0 positive. That's why it is a single pulse, single quadrant. That is which quadrant? First quadrant converter. These are the drawbacks of single phase half wave control rectifier. Please go through this point. Output is controlled only in one half cycle. Output exists only in one half cycle. Due to this, average and RMS values are less. Less power is delivered to the load. Input power factor and efficiency is less. High ripple factor. Less transformer utilization factor. Source is subject to DC nature of current. Due to this, more number of harmonics are introduced into the load. It is used only for motoring control. This is about the drawbacks of single phase half wave control. To overcome these drawbacks, then we are going for single phase, full wave or fully controlled rectifier. Before going to explaining that single phase, full wave or fully controlled rectifiers, that I will explain the next session. This session is completely single phase half wave controlled rectifier. Yes, that you have to concentrate. This is the one practice questions with respect to single phase half wave controlled rectifier with freewheel, RLE and freewheeling diode. RLE and freewheeling diode. This practice question you have to concentrate. What the average output voltage, what the average output current, that you have to concentrate. And this is for purely inductive load. Single phase half wave control rectifier with purely inductive load. What the conduction angle? What the extinction angle? What the conduction angle? Where alpha is the firing angle, that you have to concentrate. Friends, with this, with respect to module 2 rectifiers, that is AC to DC converters, the concept of single phase half wave control rectifier is completed. This is about the session.